Hello, everyone. I'm Cong from Nanjing University, and I'm very excited to be here to discuss with you how to correct the JIT compilers of modern VMs. And this work was collaborated with Yanyan. He's over there, Chang, and Zhendong. Yep, let's start it. Okay, I believe all of us agree that compilers are very critical system software in the world, and almost all the critical system software require compiler like kernel, VM, and emulators and compiler themselves. But perhaps less people know that compilers can be divided into ahead-of-time compilers and JIT compilers. AOT compilers compile program before running the program. They have extensive array of analysis and transformation passes that help them to transform source code to low-level optimized code. But JIT compilers are very different. They can only compile program while the program is running, although they are also equipped with various analysis and transformation passes like AOT compilers, but they can only compile program, a portion of a program at runtime and on demand. Because of this, JIT compilers are extensively used in various VMs like JVM, JS engines, and .NET runtimes. Often, a VM boots in the interpretation mode, and they can start up very fast, but at this time, they run very slow. At runtime, the VM monitors hard code that are frequently run in the VM, like loops and method calls and many other code structures, and compile them to optimize the binaries, but leave all the others still uncompiled, such that they can get very high peak performance with a very cheaper JIT compilation cost. Well-known JIT compilers include the C1, C2 compiler in OpenGDK and the Grout compiler in Grout VM. Okay, let's take a very simple example to explain how it works. If we have this example and we'd like to input it to the VM, when we input it to the VM, we interpret it. We interpret it from main, from foo, and then foo for many times. But if we call foo for a sufficient number of times, then the VM recognizes foo, the method foo, and the loop L as hardcode and apply JIT compiler to compile it to optimize the binaries, but leave all the others still uncompiled, like the main and bar. And next, we are going to execute the foo, and for the rest number of times. But when the loop exits, we return back to the interpreter and interpret the bar until the program exits. But very aggressive optimizations need significantly more time to compile. So many VMs support multiple JIT compilers and support tiered JIT compilation. In particular, when they discover some code are very warm, they apply a mild compiler to fast compile the warm code to well-optimize the code. But when they further find the warm code are even hotter, they apply another aggressive compiler to slow compile the program to super optimize binaries, and this is called tiered compilation. Besides compilation, there are chances that the VM bails out and turns back to the interpreter. Like when the JIT compiler compiles this loop, it assumes that I is less than 90,000. So when this loop exits, the assumption breaks, or when some unexpected conditions happen, the VM has to go back to the interpreter because they don't have any compiled code for them. And this is called de-optimization. So you see, all of this makes JIT compiler a very, very super challenging component in VM and become a primary source of bugs in VM. To test them, there are three challenges. First, JIT compilers are also very deep VM components. Second, JIT compilations are often pretty complicated. And third, the interactions between JIT compiler and other VM components are often intensive. So it sparks many existing work to test VM like this. But we realize that few bugs found by them are JIT compiler bugs, and even most cannot reach the very deep JIT compiler. And also, there are also works focusing on JIT compilers, but they did underlook the other two challenges that we have mentioned before. Compared with them, our work, CSE, can find, for challenge 1, can find 85 bugs, and all of them are JIT compiler bugs, where 53 were confirmed and 26 are already fixed. These bugs affected 3 widely used production JVMs like Hotspot, OpenGTK Hotspot, like OpenG9 and ART, and more than 20% of them are miscompulations. And for the other 2 challenges, our bugs affected various optimization paths and interactions between J compilers and other VM components, like loop vectorization, like register allocation, and like garbage collection. And we also received many effects from the J compiler teams of both Hotspot and OpenG9. So how do we achieve this? Actually, our work has recorded the mechanism of J compilation that each program running in the VM often transited between interpreted bytecode and J compiled code. And this tells us that a single code block can have multiple execution states. Like, you can start by interpretation, and then J compiled by the first tier, and then J compiled by the second tier. And at any time, you can be de-optimized to the interpretation and exit. But for the next time, you may start from being J compiled by the second tier and experience a totally different transition process. These 2 transitions are different. So if we assume very simple method-based VM that all compiled code blocks are methods, we assume we do not support other code blocks. And we only have 2 tiers, the tier 0 interpreter and tier 1 J compiler, and that the de-optimization only happens when the method exits. We can simply find that each method call is either in an in state or in a J state, and they are transited between these 2. We can also find that if we have a program with n method calls, this can form an exponentially large space with 2 different J compilation choices. And this is a big opportunity for testing, right? Because this compilation space is so large. And in this work, we call such a space compilation space modular VM. And each choice in the VM, we call it a JIT choice. Looking at this space, if you think it for a while, you can find that the key to the space is that if you run the program with any choice in the space, you should get exactly the same program results, right? This is very strong characteristics, and it actually resolves the challenging Oracle problem in testing. Let's take an example. Like we have this example, no matter how we interpret or compile the method main, full, bar, or base, the program should consistently print 2 because we have 1 plus 1 in base, right? So, with such a big opportunity and this test Oracle, how could we validate J compilers with compilation space? Actually, there are a whole lot of things that we can do. Like, if we can get the default choice of a program, we can push every method call to the J state. And in the space, it push the choice to the rightmost, right? We can also pull every method call to the in state to the leftmost. And we can also flip the state of every method call, or we can randomly flip the state of some method calls. So ideally, we'd like to explore the whole space. Ideally, we'd like to explore the whole space and cross-validate every JIT choice for each program. And ideally, they should consistently return the same results, right? So if any 2 of them produce different results, the J compiler should be buggy. And this is what we proposed. We call it CSE, compilation space exploration. If we put it simply, what we actually want to do is we'd like to interleave the interactions, we'd like to interleave the interpretations and J compilations frequently in each choice. In particular, for each choice, we'd like to run the program to program P1, and then by interpretation, and then to program P2 by J compilation, and then to P3 by interpretation, and so on and so forth. And for others, we want to apply a very different interleaving, and in the end, we'd like to cross-validate their results. And this is called a small explanation hypothesis proposed by one of my mentors, Yanyan. And he's also using this hypothesis to many work now. Yeah. So let's also take a very simple example to explain CSE. And in this example, this is a concrete example that we have found in OpenGenome. In this program, we have manipulated the compilation space by flipping the state of the last method call. We have found that if the last method call is in I or G or JJ, it consistently prints 0. That's the correct answer. But if we flip the last method call to triple G, it prints a random value. That's incorrect. So with CSE in mind, how could we realize it? That is just an approach in mind and in conceptual level. So how could we implement this? Actually, there are two very obvious options. First, we can modify the underlying VM implementations, or we can just leverage the J compiler related options. But both of these two approaches are either cumbersome or limited to the functionality of J compiler options. But both of these two implementations need very expertized VM specific knowledge to implement them. But we want something different. We want our method, we want our implementations to be practical, to be VM agnostic, and to be lightweight and powerful. So the key of our realization is to leverage semantic preserving mutations to approximate CSE from source code level. In particular, for each program P, we'd like to mutate it to a program P1. And in this mutation, we ensured that P and P1 produce exactly the same result, but with very different default choices, C and C1. And with more mutants generated, we can explore the whole space very progressively. And in the end, we compare the results of them. And in other words, we are approximating P with different JIT choices by a set of mutants, P1, P2, with their default choices. So, what we'd like to do is to devise very special mutators that can mutate a code block among different JIT or int state. And to do this, we have mutated with the help of JIT-relevant operations. Such operations are extensively relied on by JIT compilers. They are code structures that JIT compiler extensively relies on, like loops, method calls, and various unexpected conditions. And we call this JIT up neutral mutation. For example, if we'd like to mutate, we'd like to let line 6 from I to G, we can wrap it by a loop, such that it can change the state at runtime. But to avoid being optimized out, we also insert some irrelevant code that's using existing variables such that it cannot be optimized out. And in our work, we have now designed 3 such mutators, mainly focuses on mutating a code block from int to JIT, but they can also work sometimes from JIT to int. And our mutators can also generate code that preserves the semantics. Let's see the previous example. In our implementation, we mutate the state of the last method by inserting such code blocks. It is highlighted by the box. This is inserted by our code such that it can mutate the state of the last method call. Okay, this is our work. In this work, we have proposed compilation space and CSE for JIT compiler validation. We have also implemented CSE by a JIT up neutral mutation. And in the end, we also implement JIT up neutral mutation specifically for JVM by a tool called Artemis. And this is our tool. And you can see a QR code in the end. Actually, there are also some cases that the current Artemis does not cover yet, like like general JIT to int support, like floating point number support and concurrent code support. And we are expecting more developers to support them. And in the end, we also hope that CSE can be unleashed much more power by many good techniques like coverage-guided mutations, like efficient explorations, white box integrations, and novel mutators that can mutate from JIT to int. And that's all. Thank you very much.
Any questions? And please state your name and affiliation before asking questions. Thank you.
Ed Bugnon from EPFL. This is extremely impressive work, and the results are extremely impressive.
Thank you.
I guess what was striking is that you're making a number of simplifying assumptions and restrictions, right? Whole method, you have explicit mutators, source code level changes to do the mutation. It seems that you're only uncovering a very small fraction of the potential sea of bugs that we have in JVMs. Is that the right way to think about the set of unexplored and unidentified bugs that may be present right now?
I'm sorry, I need to first clarify our assumptions. Please hold on.
Yeah.
First, all of these assumptions are just used for explain the framework in this talk.
Okay.
It is not the assumptions of the whole approach, actually what we have done in our work. These assumptions are only for simplify the process of this talk.
Okay,
Can you understand?
okay, thank you. That's helpful. But your approach is to generate source code and to mutate source code, which then gets compiled and JITted and interpreted, right? This is an extremely high-level starting point, and what I'm suggesting is with a very high-level starting point, you can only have partial coverage of the set of bugs that may exist in the underlying system. There should be many, many more bugs that you cannot find that do exist, but they cannot be found because, for example, they cannot be exposed through a source level change. Is that the right way to think about this?
First, what our work just targets J compilers, right? So we have to do works to interleave J compilations and interpretations, and we want to use some interleavings to find the bugs that J compiler can miscompile a program. It compiles a program that are different from interpretation, right? So to do this, we have used mutations to do this transformation. This is the first. And second, we'd like to cover many optimizations. So we have inserted many existing code, and we have also synthesized some code from some code generators, such that all the code combined together can trigger very diverse optimizations. So we can cover many optimizations in the J compiler, like these components. I don't know if I understood you correctly.
Or maybe we can take it offline. Thank you. It was great work.
Thank you.
I guess I'm next. Petros Maniatis, Google. The numbers speak, so you have succeeded. This is about making sort of the icing on the cake. What I'm trying to understand is your solution is very specific to the implementation of the triggering logic and the optimization itself. So if a JIT compiler changes slightly, you have to come up with a new kind of code mutation that would trigger the updated JIT compiler to trigger. Is that correct?
First, I have to say that there's no bullet in the world. So I don't think there's an approach that can do anything, first. And second, our approach are basically based on the mechanism of J compilations that almost, I didn't see all, right? Almost all the J compilers in the world are, I can't find it, are like this. They are transiting between different states. And what we do is to make them to transit from one state to another state. But we don't care about how to do this. And in JVM, in JS engines, we do this by adding some code blocks like loops, like method calls. Many times the method calls to do this. But conceptually, this implementation is different from our approach CSE, and CSE can apply to almost all the VM and J compilers. I don't know if I can answer you.
Maybe I'll let someone else ask a question. I'll come back.
Okay, thank you.
All right, so the next question goes to the one above.
Hi, Brad Karp from UCL. I just wanted to ask, it seems like your work assumes that differences between these different compilations are bugs in the JIT.
Yeah.
is it possible in principle that the application whose code you're perturbing could have a bug, which then leads to sort of undefined results in the language, and that then you get different results for the different compilations because the application you're perturbing has a bug in it?
I'm sorry, first I didn't see you. Okay. So second, if I understood you correctly, are you asking if our approach can be applied to language specifications, not JIT compilers?
I don't think that's what I'm asking.
Please say it again.
I think what I'm asking is, if the application whose code you're perturbing with your approach has a bug in it, is it possible that you'll get different results in the different compilations?
Yeah, correct. That's a bug. That should be a bug because different compilations should compile this program to different code, but they should produce the same results. So if they generate different results, like if you have 1 + 1, in one JIT compilation you print 2, and in another JIT compilation you print 3.
I understand for 1 + 1. I was asking about, there could be sort of a bug in the application where the compilations give different results because of the bug in the application, because maybe there's undefined behavior of some kind.
I see. We are targeting. First, our work. Currently, our work just work for JVM, JS engine, and I don't think there are any undefined behaviors in the JVM specification because JVM is designed to be not undefined behavior, right?
So if I may, Brad, I think they are generating the application. So they are not taking any existing application.
Yes, correct.
And they ensure there's no side effect of these things. No.
I see. Thank you.
I'm sorry.
And unfortunately, we're running out of time, so we'll take that question offline.
Okay, thank you.